Well, so now we'll talk about the octahedral field stabilization energy. So this is also going to be continuously called Ligand field stabilization energy, and it's also synonymous with crystal field stabilization energy. So we're back to the octahedral geometry, but if you start out with the free ion, and you basically have the 5d orbitals that are degenerate, and then you put them into the spherical Ligand field or uniform spherical field, however you like it, then your 5d orbitals now are, again, still degenerate. And then you put it in the octahedral field, which then splits everything, again, based on electrostatics, where coming down is a stabilizing event, and going up in energy is a destabilizing event. But the point being, now we want to calculate what the energies are going to be in each of these instances as a function of the d electron count. So as we already talked about, coming down is basically the equivalent of reducing this energy down by 0.4 del O for really for each orbital, and then going up, it's the same as increasing it by 0.6 del O, and that's just recognized there. And then really the sum of those two winds up putting you back here at the center of gravity again. So again, you have to conserve energy in this process. So let's actually get to it. So now the Ligand field stabilization energy is going to be the change in energy of the d electrons due to this orbital splitting that takes place. And I kind of have it blown up a little more here. So let's consider a low spin cobalt-3 species, which is actually D6 configuration. So if you now have a D6 configuration, each electron that's going to be placed in this picture, 6 electrons end up getting placed in the T2G orbital set. So it winds up looking like you have all of those electrons now that are in the low spin geometry, and they're all spin paired. So every electron that's in there gives you basically a 0.4 del O stabilization. And because of stabilization, we put a negative sign in front of it. And that means it's a negative 2.4 del O stabilization with respect to the spherical field that you begin with. So that's one example. Let's go to copper 2, which is a D9 system. So now the copper 2 D9 system is going to fill all of the electrons in this manner, where you now have D9, but you can basically see that 6 of the electrons went into the T2G set, and then 3 went into the EG set. And then that results in the same idea, except now you basically have the 6 electrons in the stabilizing orbitals, but then you have 3 in the destabilizing orbitals. So the net change in energy with respect to sort of the spherical field is the net improvement in energy there is now minus 0.6 del O in stabilization with respect to where you started from. So you can see that's one of the rationalizations for why these molecules have ligands in these certain geometries. It's like the stabilization gain makes it more energetically accessible. And then if you go to a copper 2 system, or sorry, go from copper 2 to copper 1, now copper 1 is D10. And as you can expect, because we now filled all of those ligand field orbitals, the net result of this is that there's 0 gain in del O stabilization energy, because it's effectively a D10 system, and there's absolutely no massive advantage you get by having the molecule in an octahedral environment. But that is the fact is that is the net stabilization energy that would be calculated. So let's go into more general terms. So what happens in the top part of this table is these are all the weak field cases. And the weak field cases, remember, gives you high spin configurations. And as I said before, D1, D2, and D3 are all basically going to be high spin no matter what you do, because of the fact that you're going to just fill the lower energy orbitals first. It's only when you go to D4, D5, D6, and D7 where you can have the differences in high spin and low spin configurations, but these on the top here are the high spin configurations. So what do you gather from all of this? Well, you're illustrating in every single case here what happens if you go to high spin. So high spin, in essence, if you look at D5, you basically spread the electrons out as much as possible. And then in D6, you have no choice. You have to start spin pairing. And then you start to spin pair in D7, and then you get to D8, and then you finally have to spin pair in the T2G set. D9, you then have to start spin pairing in the EG set, and then D10 is, D10. So if you now compare that with what you have in terms of strong field ligands, so these give you the low spin configurations. Again, D1 to D3 is the same as it was in the example above. But then D4 now, you're going to fill the T2G set first, and then D5, you're continuing that process, and then D6 is all filled. And remember, I told you in some of the previous presentations that D6 is a really special configuration and makes incredibly stable transition metal compounds. And then D7, now you see what happens with the low spin configuration. You can't fill the T2Gs anymore, so then you start filling EG, and then continue to fill EG as you go from D8 to D9 to D10. And that gives you sort of the sense of what all of this looks like in terms of those are all of the possible electron configurations in the D10, in the d orbital configurations. So now if we go to the table that's presented here, and no really big surprise here, these are the ligand field stabilization energies for every possible d electron configuration in the weak field or high spin configuration. And then again, at below is for the strong field and generates the low spin configurations. And you can kind of see the net result of how this will play out. And just look at the extensive nature of the ligand field stabilization energies that are generated in all of these cases. And ultimately, it sort of shows you that across the board, except in D10, in every possible electron configuration, the strong field or low spin configurations generally have significant stabilizations to offer in going between D4 to D7 configurations. And then, as you can sort of tell, D8 and D9 and D1 to D3 all look the same otherwise, but those are the special cases. And the special cases really shows you what is the difference between the high spin and low spin configurations. And this is really all you need to know, is if you take all of the Coulombic energy, all of the exchange energy of the strong field case, as well as the ligand field stabilization energy, and then subtract that from the corresponding values that you see in the weak field case. So really, as shown here, the strong field minus the weak field, you'll see that the gains you get in making effectively a strong field or low spin complex is really the major differences occur from the D4 configuration to the D7 configuration, and they're really illustrated there. And the gains that are made are typically significant in terms of the ligand field stabilization energy, although you will see that there's other energies that do come into play here. But this is how you actually calculate the ligand field stabilization energies of every possible configuration that you'll ever come across. And then to sort of summarize everything we've spoken about with crystal field theory, things that affect the magnitude of del, and then we talked a lot about the octahedral field in particular, so del O, but it really is the oxidation state of the metal ion. Remember, the higher the oxidation number, basically the larger the del O was. And really that has to do with effectively the fact that it becomes a better Lewis acid and it makes stronger bonds, so that makes a stronger field arrangement. And the next part of this was the nature of the metal ion, but we didn't discuss this in a lot of detail. But as you go down the periodic table, del O also increases, and that's simply because the d orbitals get larger, and then they're able to overlap with the incoming ligands significantly better, and then that makes stronger bonds. And because they're stronger bonds, they actually will wind up giving you larger values of del O as you go down the periodic table. In fact, everything that's 4D and 5D all make low spin compounds. You can only make high spin compounds from the 3D series in terms of using ligand fields to control everything. And that was really the location in the periodic table. So the first row transition metals versus the second versus the third. And then of course the number and the geometric location of the ligands. So if you remember, the tetrahedral field had 4 ligands, the octahedral that had 4, octahedral had 6. And if you remember, the tetrahedral crystal field had about 4/9 the magnitude of the octahedral crystal field, and that had in part to do with the number of ligands actually matters in terms of that. And then the geometric disposal or disposition of the ligands really matters too, because that dictates what d orbitals are going to be more destabilized and which ones will be more stabilized. And then finally, the nature of the ligands, of course, matters. That's going to be corresponding to the spectrochemical theories, but specifically, and we will discuss this when we talk about ligand field theory next, is that this has everything to do with whether or not the ligands have sigma donor or sigma acceptor properties, and whether or not your ligands have pi donor or pi acceptor properties. And that dictates what d orbitals the ligands prefer to interact with, and in what ways can those interactions take place to actually help modify the magnitude of the crystal field or ligand field splitting. Okay, so that's all I wanted to discuss for today. And as I told you, next time we will definitely start discussing ligand field theory and bring sort of the molecular orbital picture back into this discussion. And thank you again for your attention.